But today, I'm very pleased to welcome Samson Abramsky from the Computer Science Department in Oxford, who's going to be talking to us today about the logic of contextuality. So, Samson, whenever you're ready.
Okay, thanks very much, Tim. Yes, and thanks to David and Tim for the invitation to speak in this colloquium. It's a pleasure to do so. So I'm going to talk about the logic of contextuality. This is joint work with Ruiz Suarez Barbosa. I'm having a problem with advancing my, I think I've, yep, sorry about this. Full screen. I think if I hopefully do this. Yes, good. All right, so I think we're still working on things related to this. A particularly interesting question is a sort of duality theory that we're currently, I think, making good progress with, but it's not quite ready yet. There's a paper corresponding to this talk which appeared in the Computer Science Logic Conference this year, and it's in the conference proceedings, but you can also find it on the archive. And I'm going to emphasize some aspects of this subject in the talk, and not talk much about the probabilistic aspects in particular. There's a lot more about that in the paper, just to keep things at a reasonable length. And also I'll try and be fairly self-contained, since I assume not everyone is into foundations of quantum mechanics and the like. So I think what is here hopefully relates to people's interests in category theory, logic, and the connections between the two. So just to begin with a little bit of background, in his famous work on the mathematical foundations of quantum mechanics, going back to the late 1920s, and which we're still using today. I mean, this is what people actually use to calculate with every day in basic quantum mechanics and everywhere in quantum information, quantum computing, and so on. John von Neumann identified quantum properties or propositions as projectors on a Hilbert space. So these are linear operators, or if you want to think in finite dimensions, we can think of them as matrices, which are self-adjoint, equal to their own complex matrices, which are equal to their own conjugate transpose and idempotent. And there's a famous correspondence between projectors and the closed subspaces of a Hilbert space. These, I should say, are the sharp properties. You can sort of go to a richer picture by allowing for sort of unsharp operators, so you admit noise and so on, but we are going to focus on this classical setting. Now, what everyone knows about quantum theory and logic is quantum logic in the sense of Birkhoff and von Neumann, which just a little while after this book of von Neumann's, he and Garrett Birkhoff, who was a founding father of modern universal algebra and lattice theory, wrote this paper, The Logic of Quantum Mechanics, and they proposed the lattice of closed subspaces as a non-classical logic to serve as logical foundations of quantum mechanics. And people have been studying that in various ways ever since. I have to say, in many ways, it hasn't been a great success story, certainly as far as providing useful tools for current day quantum information, quantum computing, and even quantum foundations are concerned. The lattice of closed subspaces is something like a logical lattice, but famously it fails to be a distributive lattice. So logic is not all that nice. So a huge amount of work has been done in this tradition, but as I say, it's had relatively little impact on either physics or on quantum information and computation. One of the key reasons for the latter is the lack of a good account of the tensor product, which is ubiquitous in quantum information and computation. When you start talking about Alice and Bob and all those sort of protocols and things like Bell's theorem and so on, then we're generally using tensor products. Now, a different approach was proposed by Simon Kochen and Specker, who were both logicians by trade, in their seminal work on contextuality in the 1960s, which was based on what they called partial Boolean algebras. And this is going to be the setting for what we're going to talk about in this talk today. So I should say that, yeah, so I mean, just to give a flavor of the difference, Birkhoff and von Neumann used this correspondence between projectors and closed subspaces. Now, closed subspaces are certainly closed under intersections, but if we think of a kind of operational meaning for projectors, as they appear in the sort of operationally in the formalism of quantum mechanics as basic kinds of measurements or as kind of parts of measurements, then they have a clear physical interpretation that way. But if the projectors don't commute, then the intersection of their closed subspaces does not have a clear operational meaning, which was kind of admitted by von Neumann from an early point. And he personally kind of gave up working on quantum logic in that sense. The point about what Kochen and Specker did, as we'll see very shortly, is that they only focused on the physically meaningful things, which led to this idea of partial Boolean algebras. Well, just to say a little bit about the general setting here and what this is all about, the general concept here is contextuality. So from the point of view of quantum computation, since this is what's kind of having an impact on our world today, or beginning to, is that the key question is to characterize those tasks where there is provable quantum advantage, i.e. the task can be performed provably better using quantum resources rather than with purely classical resources. And this focuses attention on what is non-classical about quantum theory. And in particular, contextuality, in many ways, is the essence of what is non-classical about quantum mechanics in its purest form. And it may be that really, it may be the whole story of non-classicality and quantum advantage, or it may be an important part of the story, but it's certainly at least the latter. So it's a key signature of non-classicality. Non-locality, as famously in Bell's theorem, is a special case of contextuality from a mathematical point of view. And it's at least highly implicated in many of the cases that we know of quantum advantage. So let me mention as a recent example, there's been very nice work on provable quantum advantage with shallow circuits, unconditional on complexity theory assumptions. This is work of Bravy, Gossett, Koenig, and others. And some work with my student Sivert Osnes has been doing. I mean, what they do in those constructions is to leverage classical contextuality constructions into shallow circuit instances which show quantum advantage. And it seems there's a much more general story that can be told of how to turn contextuality arguments into such instances. This is what my student Sivert is working on. So what is contextuality? Well, my preferred slogan for this is that it arises where there's a family of data which is locally consistent but globally inconsistent. So we think of things that patch together locally but don't patch together globally. So for the audience at the Topos Institute, I don't need to sort of stress that this sort of sounds exactly like sheaf theory, and indeed that's why I've taken a sheaf-theoretic approach in studying contextuality, which turns out to work very well. But I'm not going to emphasize that aspect so much in this talk, although it will be there kind of in the background. Okay, so what are partial Boolean algebras? A partial Boolean algebra is given by a set with constant 0, 1, a reflexive symmetric binary relation, which is read as commeasurability or compatibility. And we have negation as usual, which is a total operation. and we have the usual conjunction and disjunction and an or, but these are now partial operations whose domain is given by this commeasurability relation. Actually, before I should maybe just go back a moment to the motivation here with projectors. As you can easily verify, the product, the composition of two projectors is a projector if and only if the projectors commute. So, and it's exactly when they commute that operationally the composition has a good meaning, because you can then perform both measurements on the same system prepared the same way, and it's meaningful to do that. If they don't commute, then you don't get a projector. This is why the connection with closed subspaces is somewhat deceptive, and why the Birkhoff von Neumann approach leads to things that aren't really operationally of a clear meaning. The point of view of Kochen and Specker is precisely to insist on only looking at things that are physically meaningful. So if you think of commuting projectors, then you actually get a Boolean algebra there just for commuting projectors. And then in the case where they don't commute, you say that the conjunction is not defined. So this is what brings us to these partial Boolean algebras. Anyway, to complete the definition of partial Boolean algebras, they have to satisfy the following property, that every set of pairwise commeasurable elements must be contained in a larger set of pairwise commeasurable elements, which forms a total Boolean algebra under the restrictions of the given operations. That's a bit of a mouthful, and it's a bit second order. You can make it more elementary by giving the conditions in a more finite tree way. One thing to just comment on the side is that notice there's this emphasis on this pairwise commeasurability, and it's a binary relation. This is because if you have a family of projectors, the property of them being pairwise commuting is a pairwise condition. If every pair of projectors in a set is commutes, then the whole thing is a commuting set of projectors. We'll come back to this. I mean, this is related to what's sometimes called Specker's principle, which is that this binarity is an important feature of quantum mechanics. It is possible to consider more general schemes, but for the direct connection with quantum mechanics here, then we'll follow this binary approach as Kochen and Specker did. So, and just to in terms of terminology, I mean, when we just say Boolean algebra, we're always mean total Boolean algebra, and when we mean partial Boolean algebra, we'll say partial Boolean algebra. And the key example, as we've been saying, is the projectors on a Hilbert space. And the operation of conjunction, the product of projectors, becomes a partial one, only defined on commuting projectors. And then I should say the complement, the negation operator, so the complement of P is 1 minus P, if you think of it in operator terms. That's always defined and always gives you a projector. And when things are suitably defined, then you can define also a disjunction by De Morgan duality. Okay, so that's what a partial Boolean algebra is. And morphisms of partial Boolean algebras are maps preserving commeasurability and the operations whenever defined, and this gives us a category of partial Boolean algebras. These were the objects that Kochen and Specker worked with. I should say in a famous paper from 1967, the 50th anniversary was celebrated with various conferences around the world a few years ago. So what did Kochen and Specker do? In that paper, they showed that contextuality is inherent in quantum mechanics, even in finite dimension, as soon as you have a space of dimension at least 3, and moreover can be formulated in logical terms using this notion of partial Boolean algebras. And the link, just to emphasize again, is with this canonical example of the partial Boolean algebra P of H, projectors on a Hilbert space. So here is the original Kochen-Specker formulation of contextuality. So we might say, is this okay, this is a partial algebra, but is that partiality really serious? Could we somehow expand the definition of things? Could we embed the partial Boolean algebra of projectors into a normal kind of total Boolean algebra, and then we could still be, reconciled with classical logic and a classical way of looking at things. So their key result is a negative result. There is no such embedding as soon as the dimension of the space is at least 3, and of course also for infinite dimension. Now, in fact, they considered, and by the way, it's a beautiful paper, which is nice to read, and it's sort of, you could say it's incipiently sheaf-theoretic, but without using those tools. So they consider the hierarchy of increasingly weaker forms of non-contextuality. So, the idea of being able to embed the partial Boolean algebra into an ordinary Boolean, total Boolean algebra is a form of non-contextuality. Everything is classically explainable. We're just only seeing, for some reason, a part of a normal classical structure. So that's non-contextuality. And then when you can't do it, that's when you get contextuality. So here are their notions. A can be embedded in a Boolean algebra. Then there's a homomorphism, not necessarily, there's a homomorphism to some Boolean algebra whose restriction to each Boolean subalgebra of A. And notice that, there are a lot of Boolean subalgebras of a partial Boolean algebra. You can start off with any sort of set of pairwise commeasurable elements and get a sub-Boolean algebra that contains them. That was the property that we had in our definition. So every restriction is an embedding. And finally, there is just a homomorphism of any kind to some Boolean algebra out there. So these are all weaker forms of we're asking for less and less as we go down this list. So saying you can't have that becomes stronger and stronger. So the first condition, just using familiar facts about Boolean algebras, is that there are enough homomorphisms to the 2-element Boolean algebra to separate elements of A. So I guess everyone remembers some basic facts about Boolean algebras. So you can, for a Boolean algebra, there are always lots of homomorphisms into the 2-element Boolean algebra. These are essentially the truth valuations. They're enough to separate the elements of the Boolean algebra. There's going to be some homomorphism which makes one element true and the other one false. This is to do with this is connected with sort of maximal ideal theorem and so on, ultrafilter theorem. So in the usual world of Boolean algebras, there are plenty of homomorphisms to 2, and that's equivalent to saying that there's an embedding in a Boolean algebra. Because in fact you can then embed A into this power of 2 that would it will be an embedding because you have enough homomorphisms there to separate the elements. And the third one is, we're getting a bit desperate by this point. All it's asking, if we say there's a homomorphism to some Boolean algebra, since every Boolean algebra has homomorphisms to the 2-element Boolean algebra, it's actually equivalent to saying there is some homomorphism to the 2-element Boolean algebra. So therefore, the strongest contextuality property is there is not even one homomorphism into the 2-element Boolean algebra. So that's what Kochen and Specker prove. So that's a very strong form of contextuality. Now, one of the things that kind of subsequent work has shown, and it's been quite a feature of the things that I've been doing, is that there's a whole hierarchy of different notions of contextuality, and they prove useful in various ways, and you can also quantify things using inequalities and so on, but this is the strongest form, and this is what Kochen and Specker prove. Let me make one other sort of comment in advance. I don't know about you, but sort of one somehow feels that leaving aside questions of set theory, Boolean algebras are fairly simple beasts, really. Finite Boolean algebras are power sets and so forth, which is not entirely fair to Boolean algebras, but they're not that difficult in many ways. But partial Boolean algebras are really quite subtle, and we'll see various signs of that as we go along. Anyway, this strong contextuality property, not even one homomorphism to the two-element Boolean algebra, we'll call the KS property, Kochen-Specker property of a partial Boolean algebra. So a partial Boolean algebra witnesses contextuality in this strong form when it has this KS property. So something, alas, I don't have time to talk about, but there's a wonderful paper. So I mean, we're talking about Boolean algebra, so we're thinking of Boole when we use that terminology. Boole was a pioneer of both logic and probability, and Boole wrote a great paper in the 1850s, which is still very readable actually, where he asked for conditions of possible experience, which has been suggested was maybe a bit of a kind of jokey Kantian terminology for in relation to probability distributions. And it turns out that he was asking basically for inequalities that would characterize, probabilities on events under various logical conditions. And this turns out to be equivalent to Bell inequalities. So that's what's behind Bell's theorem and is one of the major tools of modern quantum information. So Boole and Bell are actually very close. Logic and probability are in there all the way. So here, so that was conditions of possible experience, because that's really the inequalities that bound what could happen in the circumstances where you have a classical probability distribution explaining everything, or in more traditional terminology, a kind of hidden variable model. So here I'm talking about conditions of impossible experience. So here is a physically remarkable result from the same paper by Kochen and Specker, which I think is still, to get to get a sort of feel for this result is not so easy. I mean, I say physically remarkable because it says something remarkable about our physical reality, I think, given that quantum mechanics is, as is often said, the most highly confirmed physical theory that we have, confirmed every day with experiments and being turned into technologies and so forth. And given that, partial Boolean algebras of projectors on Hilbert space have this KS property, I mean, that's really what they were showing. So they are a basic instrument, a basic part of the formalism of quantum mechanics. So what they showed was that it's equivalent that a partial Boolean algebra is Kochen-Specker, and that there is a propositional contradiction. So in other words, something that has no satisfying assignments, and an assignment, a propositional formula. I mean, it won't be as simple as A and not A, but it'll be something that, however you assign values to the variables, you can't make true. And a way of assigning to the variables in it elements of the partial Boolean algebra, such that that is actually true in the Boolean, under that valuation in the Boolean algebra. And you may be saying, well, but this is a partial Boolean algebra, how are you going to evaluate a formula? And the point is that this is such that everything you need to be defined to evaluate that formula, all the conjunctions and disjunctions you encounter, are well defined in the partial Boolean algebra. So it all makes sense. You get a value and it evaluates to 1, the top element, true. So it's a contradiction and it evaluates to true in this structure that is a fundamental part of our best description of physical reality. I think one should find that challenging. What it's saying is that the event algebra of quantum mechanics cannot be interpreted globally in a consistent fashion. This is coming back to the mantra of locally consistent but globally inconsistent. So our local observations, which, remember, I mean, this is a direct abstraction of real observations of real measurements, cannot be pieced together globally by reference to a single underlying objective reality which says what value everything has. The values that they reveal are inherently contextual. And in the setting of partial Boolean algebras, you can think of the context as the Boolean algebras, the things that sit inside, which are compatible and can be measured together. Those are Boolean algebras. Everything within one of those looks classical, and that's what we can observe directly, but we can't patch them all together to a single underlying objective reality. So how can the world be this way? Well, people are still discussing that, and to my mind, no fully, I mean, there are many philosophical interpretations, none of which I find help me much. I think it's more interesting and perhaps more fruitful to see what we can do with these remarkable phenomena. And the earlier remarks about quantum advantage and so on relate to that. Okay, so what does this category of partial Boolean algebras look like? So there's a very nice paper by Chris Hernan and Benno van der Berg, Non-commutativity as a colimit, in which it's shown that in that category, which is, let me emphasize now, and we'll see more examples of this soon, is very different to the category of Boolean algebras, although the category of Boolean algebras is a full subcategory. But it's shown that every partial Boolean algebra is the colimit in this category, PBA, of its Boolean subalgebras. Now, what are colimits in this category? Well, coproducts have a very simple direct description. The coproduct of two partial Boolean algebras simply take the disjoint union and glue the 0 and 1 elements together. But otherwise, no commeasurability holds between the elements of A and the elements of B. By the way, this is a much simpler description than we have for coproducts in the category of Boolean algebras, because in Boolean algebras, everything is total. And given something in A and something in B, you have to be able to form their conjunction or their disjunction. So you end up with something that's a lot more like a tensor product. And if you think of stone duality, you can kind of see why that's going to be the case, because coproducts on the algebra side, the Boolean algebra side, will correspond to products on the spatial side. So here, coproducts are really simple. But co-equalizers and general colimits are not so simple, and they were shown to exist by Hernan and van der Berg by an appeal to the adjoint functor theorem. So one of our contributions in this paper is to give an explicit construction of the needed colimits. I should say, by the way, that there was an annoying remark by one of the referees of our paper saying, well, but couldn't you extract this construction from the adjoint functor theorem? Well, I hope as experienced category theorists, you will all say no, no, and again no, because the adjoint functor theorem does not give explicit descriptions. In fact, there's a famous discussion or rant, perhaps, by Peter Johnston in the preface to his book, his original Topos theory book, where he sort of speaks at some length about the difference in, well, actually about the uselessness of the adjoint functor theorem. I'm certainly not going that far. It's very useful, but you get a lot more information from a constructive presentation, and we are able to work this construction that I'm just going to show you quite thoroughly in what we do. In fact, what we're going to prove a somewhat more general result, which freely generates from a given partial Boolean algebra a new one, where prescribed additional commeasurability relations are enforced between its elements. This is obviously of interest if we are trying to move towards something more like a total Boolean algebra. So I'm going to, right, so here's the result first. Given a partial Boolean algebra and an arbitrary binary relation on its underlying set, there's a partial Boolean algebra we write like this, A extended with this relation, such that firstly, there's a morphism from the original partial Boolean algebra into this new one we've constructed, which does turn all the instances of that relation into compatible elements in the new partial Boolean algebra. And moreover, it's the free thing which does that in the obvious sense that for every homomorphism which turns instances of this relation into compatible elements, it factors in a unique way through this Ito map. And as I say, the result is we're going to prove it constructively by giving proof rules for commeasurability and equivalence relations over a set of syntactic terms generated from A. This is not so lovely, but it is useful, as I say. In fact, we even start from a set of preterms and also give rules for defining this. So I'm not going to spend a long time on this, but I'll show you the construction. So here it is. We start with the elements of the algebra we started with, and we formally kind of have the generators, this iota notation as these preterms, and this down arrow means, so we have terms, we sort of generate a lot of terms, some of which may be well-defined elements in the new partial Boolean algebra and others not. So we have a down arrow predicate to mean this is a well-defined term. We have this this binary dot thing to mean the commeasurability relation we're building, and we have this equivalence to mean is an equal element in the. So it's a kind of term algebra construction, but with partial algebras, things are always a bit more delicate. The fact that the domain of the operations is kind of itself part of the structure makes it actually a bit easier to be clear about what's going on. So we throw all of these three relations into a single inductive definition, and we make this inductive definition. So if you think about the sort of properties you would want, I mean that this should be an equivalence relation, that it should be congruence with respect to compatibility and various other things. Then I mean negation is meant to be total, so and so forth. So the only one that maybe needs some explanation is this one down here on the first one in the bottom row. I mean, what we're saying here is that if we're in one of these sub-Boolean algebras, then all the usual equations of Boolean algebra should hold, provided that, you know, everything is well defined. So if you have if you think of just of the ordinary theory of Boolean algebras, terms in some variables, and we can prove in the ordinary theory of Boolean algebras that some Boolean expression phi is equal to another Boolean expression psi, and we're going to plug in elements which are pairwise commeasurable, so everything's going to be well defined. Then when we do that substitution, the resulting things will be equal inside the partial Boolean algebra, and that's because they're actually sitting inside a sub-Boolean algebra, and then the ordinary laws of Boolean algebra apply. I mean, you could break it down into a bunch of equations, but this is a kind of more from the usual theory of Boolean algebras, but this is a more streamlined way of saying that. So that's the inductive construction. In fact, a variation of this construction is also useful, where instead of just forcing commeasurability, you also force equality by the additional rule. Although I should say that forcing commeasurability, since everything is kind of interlinked here, as you see in this inductive construction, may also force new equations as well. In any case, if you want to force equality for the given relation, then you just add this rule. This is a sort of part of the flexibility of this method. And this builds another partial Boolean algebra we write like this. And then there's the corresponding to be expected universal property, where now it's universal with respect to turning this binary relation into actual equations. And we can use that in a pretty straightforward way to give an explicit construction of co-equalizers, and we already know how to do coproduct, so we get general co-limits in that way. Okay, so now, I mean, I've already sort of talked about some puzzling things. Now let me give you an apparent contradiction and wait for you to tell me what's going on, perhaps. So as we've said, the category of Boolean algebras, the usual category is a full subcategory of partial Boolean algebras. And as I told you, we know from Hernan and van der Burg that A is the co-limit in partial Boolean algebras of its Boolean subalgebras. Now, the category of Boolean algebras also has a nice algebraic category. It has co-limits. So we could take the co-limit in Boolean algebras of the same diagram and the inclusions of Boolean subalgebras and the inclusions between them. Now, because of the universal property of co-limits, well, the cone from D to B is also a cone in partial Boolean algebras. Hence, there must be a mediating morphism from A to B. But the whole thing about Kochen-Specker results is that in general, there aren't going to be homomorphisms from partial Boolean algebras to Boolean algebras. So this is to so who would like to resolve this quasi paradox? Well, I won't belabor the point. I mean, it is a nice point, because it is actually, if you sort of look at standard accounts of Boolean algebra, Boolean algebraists always insist that at least 0 is not equal to 1. But if they were category theorists, they wouldn't do that. Because, of course, from the point of view of category theory, Boolean algebras is a nice equational variety of algebras over set. And as such, it's complete and co-complete, but it also inevitably admits the one-element Boolean algebra in which 0 equals 1. And in fact, and of course, this is nothing other than the sort of the Lindenbaum algebra of an inconsistent theory. I mean, 0 equals 1 is exactly inconsistency. And of course, the one-element Boolean algebra is the single Boolean algebra, which is an exception to the rule that they all have homomorphisms to 2. There can't be a homomorphism from 1 to 2, because it has to send 0 to 0, 1 to 1, and they're the same thing in 1, and they're not in 2. So in the case of a partial Boolean algebra with a KS property, then what we infer from this is that the co-limit of its diagram of Boolean subalgebras must be 1. And then everything makes sense. And in fact, we can turn this into a theorem. So let A be a partial Boolean algebra, then the following are equivalent. A has the KS property, and the co-limit of the diagram of Boolean subalgebras of A in the category of Boolean algebras is the one-element Boolean algebra. So in fact, therefore, we can formulate this property directly for diagrams of Boolean algebras without referring to partial Boolean algebras at all. We could now, a nice way of thinking about this, I think, is that we could say that such a diagram is implicitly contradictory. And in trying to combine all the information together in a co-limit, we obtain the explicitly contradictory one-element Boolean algebra. We kind of, as it were, follow through the chains of inference from the different pieces of information that would eventually lead to a contradiction. And when we sort of mod out by the equations, we end up with the one-element Boolean algebra where everything collapses. And now we can appreciate the point about a partial Boolean algebra, which is a very non-trivial thing. It includes all these P of H's, which are used every day in quantum mechanics, is that they hold all this implicitly contradictory information together in a single structure and in a very non-trivial and very useful way. Okay. So, by the way, if anyone does have questions along the way, I'm perfectly happy to take them, particularly if it's, to explain something better, but otherwise I'll plow on. Okay, so we now want to consider the relationship of the KS property to this construction we were just describing, the free extension by relation. So if you think about it, we could extend a given partial Boolean algebra by the universal relation where everything is related. And that's just a way of saying make everything compatible. And so it's sort of pretty immediate that it means the same thing to have the KS property, and that when we do that, then, and we make everything commeasurable, and we form all that, we sort of no longer keep these potentially contradictory things separate from each other, everything does collapse, and we end up with the one-element Boolean algebra. So this is actually fairly immediate. Okay. All right. So now we come to an interesting point. I mentioned earlier that I was a bit critical about traditional quantum logic. One of the things it's never really done is given a satisfactory account of tensor products, which are a fundamental way of combining subsystems, which is used all the time in quantum information and quantum computation. You can do, I mean, technically, a lot of things can be done with commuting subalgebras rather than tensor products, but in finite dimensions, it's the same thing, and tensor products are extremely useful. And of course, if we think of the connection with monoidal categories and so on, then, as in categorical quantum mechanics and similar things, then this is a very natural construction in quantum mechanics. So what I want to say something about here is sort of where we can see non-classicality emerging through the use of the tensor product. So as we've already said, the KS property arises in P of H if the dimension is greater than or equal to 2. Well, that says that it doesn't arise in the two-dimensional case, just the two-dimensional complex vector space. And actually, if you can work out pretty explicitly what the projectors on that, which is the space of qubits, by the way. A single qubit lives in C2. And if you work out what projectors are in that, well, if you think of subspaces and bases, then in a two-dimensional space, you choose one unit vector, and then it has a unique orthogonal vector, or projector, I should say, really, and then you span the whole space and you're done. So, and that forms, those two things with 0 and 1 form a 4-element Boolean algebra. And these can't overlap. That's the important point. If you have two different orthonormal bases, they're either the same, or because if one of them is also in the other, then so would its complement be, and then then they would be the same. So you actually get a disjoint union of uncountably many copies of the 4-element Boolean algebra, the co-product of lots of 4 copies of the 4-element Boolean algebra. And one thing that is clear is that of course you can take any sort of valuation of of each 4i for each I that you like in a 2-element Boolean algebra. You basically choose one of the vectors in the orthonormal basis to be true and the other to be false. And then by the co-product properties, you just glue all those together and you have a global valuation of the whole thing. So you have lots and lots and lots of homomorphisms into the 2-element Boolean algebra. So it very much does not have the Kochen-Specker property. Now, one of the key points now, I mean, although they showed it does hold in 3 dimensions, and it's actually there's a sort of still an ongoing. We know that they had 117 vectors in their minimum in their construction, and then this was brought down to 31 by Conway and Kochen. On the other hand, there's a known lower bound that you need at least 21 vectors, and we don't know exactly what the minimum number is, but perhaps it's one of those questions that, by the way, that involved lots of computation. So it's one of those questions which is intriguing, but probably not terribly important. So from our point of view, the interesting thing is that you can see, as it were, a non-classicality emerging from the very classical, in a sense, P of C2, which is 1 qubit. And then, the first thing we do in quantum computing and quantum information is to form, is to form multiple qubits, which we do by forming the tensor product. So we can take 2 copies of C2 and form their tensor product, which is, of course, same thing as C4. And that does, the Kochen-Specker property does hold for C4. So this is a kind of fascinating thing. Can we spot somewhere in this tensor product where where this property kicks in? And we can phrase that question very nicely in categorical terms. So we know that Hilbert space is a nice monoidal category. You have to be a bit careful here about what the morphisms are, but in any case, there is a functor, if you choose the right morphisms, into partial Boolean algebra, which is this P construction. So go from H to P of H. And what we're asking is this functor strong monoidal? In other words, can we capture the force of this tensor product by a construction on these partial Boolean algebras? And if we could, we would have a complete logical characterization of the Hilbert space tensor product, which I think would be a very interesting step towards giving logical foundations for quantum theory in a form useful for quantum information and computation. I'd love to be able to give you an answer to that question. I don't have one. We'll have some approximations to it. So how can we form tensor products of partial Boolean algebras? So in that Hernan and van der Berg paper, they did describe a monoidal structure. And what they do is you look at the Boolean subalgebras of A and B. Remember that A is the co-limit of its Boolean subalgebras, and so for any partial Boolean algebra. So you look at the partial Boolean algebras the subalgebra, Boolean subalgebras, and you form their co-products in the category of Boolean algebras. So you do allow mixing of the the things from C and the things from D, because it has to be a total Boolean algebra. And then you take the co-limit over all of those in the category of partial Boolean algebras, of course. And again, obviously, they use the adjoint functor theorem, but we can apply our general construction to give a more explicit description of it. So what we do is we take the simple co-product of partial Boolean algebras, the disjoint union, and then we extend commeasurability by saying everything in A is commeasurable for everything with everything in B. And well, that's already a well-defined thing, and we define that to be the tensor product. And it's actually quite easy from the universal property to show that this exactly captures the construction that Hernan and van der Berg gave. So that's nice, but I mean, is it going to do what we want? And what we can say is that there's a lax monoidal functor from Hilbert spaces to partial Boolean algebras with respect to this tensor product of partial Boolean algebras. So there is an embedding here, and you take the factors and embed them in, you take the projectors and they obviously embed in the tensor product as these local projectors where you just tensor with the identity on the other side. And then that gives you a morphism of the appropriate kind. But this embedding is far from being surjective. So if we go back to our example, and it's not such a big, in a way, well, I mean, it's not such a big example in a sense, but really understanding it would be, I think, a real step forward. If we take, both sides to be C2, the qubit space, and as we've seen, it's certainly non-Kochen-Specker, but there's no such homomorphism. And by the very description here, since in terms of this compatible extension, A and B both had homomorphisms into 2, and then certainly since 2 is a total Boolean algebra, it will participate in this universal property, and there will be a homomorphism into 2 from this. So it certainly does not satisfy the Kochen-Specker property. So it's certainly not capturing P of C4. Now, there's a very nice result by Simon Kochen in a quite recent paper that the images of P of H and P of K in the finite dimensional case generate the whole of P of H tensor K. Now, he actually, unfortunately, uses this to justify the this thing that we've this claim that doesn't actually work. And the gap is that the more relations hold in here than hold in this tensor product of partial Boolean algebras. So again, that sort of says, can we capture what those additional relations are? Another way of putting the same question, and with the extra subtlety that because it's a partial structure, issues of definability or partiality come in as well. But nevertheless, I think the result is very suggestive. So it poses this challenge of finding a stronger notion of tensor product. Okay, so this is where we're heading, although unfortunately we won't get all the way there. So there's an important, if we go back to our construction and sort of chase through what's going on in this inductive definition, probably this isn't going to be very instructive, but I mean, what we're basically saying here is that if you look at the relation between having an element well defined and having its sub-expressions defined, and you apply that to the this construction for the tensor product, this weak tensor product, as it were, then if T can be derived, if T well-defined can be derived, then the same can be derived for its subterms. And this is simply too strong a constraint to capture the full logic of the Hilbert space tensor product. This is one of the, and it's good to sort of focus this issue in a concrete way. Consider two projectors, pure tensors, P1 tensor, P2. So we're in Hilbert space here, or in projectors on Hilbert space. We have two pure tensors, P1 tensor P2, Q1 tensor Q2. So to show that they commute, you obviously need a conjunctive requirement. P1 commutes with Q1 and P2 commutes with Q2. On the other hand, if they're orthogonal, then in a trivial way they commute, but in an important way. And in that case, we have a disjunctive requirement. As soon as P1 is orthogonal to Q1 or P2 is orthogonal to Q2, then, because of bilinearity, then the two projectors, P1 tensor P2, Q1 tensor Q2 are a commute. So and so even though some subterms don't commute and therefore wouldn't be well defined, that sub-expression wouldn't be well defined, this larger expression is well defined. And in fact, this idea that propositions can be defined even though sub-expressions are not is emphasized by Kochen, and is also implicated in that, when I was pointing out as a physically remarkable fact, the conditions of impossible experience, these contradictions, propositional contradictions, which are made true in partial Boolean algebras, and all of whose and actually which we are able to evaluate. The trick roughly is that you evaluate to true on various sub-Boolean algebras on a conjunction of propositions. The conjunction wouldn't be, you can't just mix all the things in them, but each of the conjuncts is true in its own subalgebra. Classically, if you took the conjunction, you would get a contradiction, but they've all been evaluated to true, so they all go onto the top element, and the top element is always shared between all the Boolean subalgebras, so the conjunction of lots of copies of one is one. So maybe that gives an idea of how that actually works. Okay, so what we're going to introduce now is something we call the logical exclusivity principle. Now, the exclusivity principle has been, this and similar principles have been discussed quite a lot in the quantum foundations literature recently, mostly in probabilistic terms, and you'll find a much more extensive discussion of this in the paper. But here we'll focus on a logical exclusivity principle. So the idea is to have a notion of exclusivity, to have a positive way of explaining how you could have things which are where a larger expression is defined, even though some expressions wouldn't be compatible. So you say that two events are exclusive, and I write it with this orthogonality, if there's some pieces of information, some piece of information C, such that one of them entails C and the other one entails not C. So they can't both be, the idea is, they can't be any circumstances in which both are true, because they, there's some definite thing out there which one of them says is the case and the other says is not the case. If you want to think about measurement, suppose we're measuring various sets of variables, and maybe the kind of sets of variables we're measuring are not all compatible. But if in one case, but let's say in both cases you measure a variable x, and in one case you get that x is 0, and in the other case you get that x is 1. Even though in the first case you're also measuring x with y, and in the second case you're measuring x with z, and y and z aren't compatible, but nevertheless there's some definite piece of information that they disagree on. Now you might say, why isn't this by the way, what does entailment mean in the partial Boolean algebra? Well, importantly, to say that one thing entails or is less than or equal to another is to say that they're compatible, and then you can use the usual kind of lattice theoretic rendition of the inequality. So to say that, you would normally say that this orthogonality just says that that A meet B or A and B is 0. And of course, in a Boolean algebra, that would be equivalent. But here, we're not assuming that A is compatible with B. So we're allowing things to be exclusive, even though they're not commensurable. And we say that a partial Boolean algebra satisfies this logical exclusivity principle if any two elements that are logically exclusive are also commensurable. So then it does make sense to combine them. And so we have a full subcategory whose objects are the partial Boolean algebra satisfying this logical exclusivity principle. And in fact, it turns out that there's a condition that's been studied more classically, because in general, because of the compatibility and the definition of the order, it isn't necessarily the case that this less than or equal to is transitive in a partial Boolean algebra. Compatibility is very much a non-transitive relation. Just think of projectors. In fact, logical exclusivity it turns out to be equivalent to transitivity, but in many ways, it's for our purposes more intuitive to talk in terms of logical exclusivity. And to sort of keep a good check on our most important examples, the P of H's are always transitive or satisfy logical exclusivity. It's actually a nice exercise to convince yourself that P of H does satisfy logical exclusivity. You need to find the right way of looking at it. But anyway, the proposition is that if A is a partial Boolean algebra, then these two conditions are equivalent. And so, as we've just said, P of H is satisfy this exclusivity principle. Now, of course, we can form the partial Boolean algebra with this given orthogonality relation that's already intrinsically defined. So by doing this extension, we're forcing everything that's orthogonal to be commensurable. On the other hand, I mean, that certainly means by, from the way the construction is defined, that everything that was exclusive in the image, in A, and therefore in the image of eta, will be commensurable and therefore will satisfy the exclusivity principle. We may end up in this extension generating other stuff which doesn't satisfy the exclusivity principle. However, we can again adapt our construction to show that one can freely generate from every partial Boolean algebra a new one that does satisfy logical exclusivity universally.
Yeah. Can I interrupt very quickly? I'm just aware of the time, so it's coming up to an hour. Would you be happy to maybe pause for a little bit, do some questions, because I've seen some questions, and then afterwards, if you're happy to, you can carry on speaking, finish off your slide.
Okay, yeah, nice absolutely, yes. And I apologize for having been a bit, I've been trying to explain things, which is always dangerous, but yeah, I'm very, very happy to take questions. And after that, I can either, if anyone's interested, I can then give the last few slides, or we can leave it at that. But anyway, very happy to take questions now, yes.
It would be very nice for you to continue afterwards. So David Myers had a question, so I'm going to unmute him so he can ask that one.
Hi.
Hi.
Thank you. This has been a really interesting talk. So my question was, how strong is the relationship between partial order index diagrams of Boolean algebras and partial Boolean algebras?
Coming from a category as sheaves, Topos's point of view, one first thing is there a direct? I think there is something a bit subtle, because the operations are, they're partial operations, but they are, as it were, global operations. So, so therefore, it's the same operation that may, appear in different places, as it were. And in a way, this transitivity or logical exclusivity is pointing at that. So I think there's, I mean, it's, you know, it's a co-limit, so you've evaluated things. So I think there's more information than just you would have in the diagram. I hope I'm kind of answering the question you had in mind, but I think there's, in a way that is a bit hard to get, you know, exactly clear. There's more information than just in the diagram of, yeah.
Thank you.
Because, I mean, in fact, this whole thing of extending and then this transitivity is that things are reaching across different contexts. I mean, that's really what this exclusivity principle is about. So the first idea, which in a way goes back to the, you know, Niels Bohr picture, is that we can only talk about individual classical contexts and everything else is meaningless. But actually, we can and do talk about more than that, you know, which is why, you know, we have, well, actually, the whole contextuality thing means talking about several contexts and what happens, you know, in the relations between them. But the exclusivity is even kind of giving a bit more specific information. There's a precise sense in which you get more from this logical exclusivity than we get in the usual kind of Bell scenarios, for example, that you would have for Bell's theorem. So I hope that's kind of addressed the question. But I mean, in fact, I'd love to have a better answer as well. I think it's a very good question.
Thank you.
Okay, thanks. And we've got another question here from Andreas. So I will unmute you as well.
Okay, thank you. A question about commutativity of tensor products. So you have this example, P1 tensor P2,
yes,
and Q1 tensor Q2, and sort of the obvious condition is this conjunctive, each side commutes. But then there's this other case where one side gives a product of 0, and then you don't care what happens on the other side.
yes.
It occurs to me there are at least one other case that has come up in real examples. I think in some of David Merman's examples of Kochen-Specker phenomena, where on one side they anti-commute, and on the other side they also anti-commute, and you get two minus signs to cancel out.
Yes.
So I'm not particularly worried about that. What worries me is that if I see one more case where things happen, then maybe there are some more and some more and some more, and the thing starts to look a little bit messy. Is it in fact messy, or have we pretty much gotten to the end of all the things that can cause commutativity?
It's an interesting point. I mean, I don't have a definitive answer in a sense, you know, because I think I mean, I was hoping, the original hope was that logical exclusivity would let one get hold of this tensor product, which would be a pretty good verification that it was the right story. But we don't quite get there, as well as, you know, I'll kind of explain in the remaining slides. It's a very good question. The case you mentioned about I mean, this is with the Paulis, and that's used enormously in many. I mean, the sort of as you say, the sort of Mermin construction, or the Perez-Mermin square, as people, is one of the most used examples. A beautiful, I mean, incidentally, there are now, I mean, as I was mentioning briefly at the beginning, there are now beautiful connections between those kind of arguments and quantum advantage, where, you know, it's not an obvious connection. You can turn the Perez-Mermin square into an instance of shallow circuit that has provably, you know, where you have provable quantum advantage. So those things with Pauli's are very important, and they're sort of pervasive in quantum computing. So yes, the fact that, I mean, you know, things are controlled somehow by, you know, I mean, actually you have Z4, you know, if you think of the multiplicative group of I, but then, you know, for the and a lot of phenomena that you get out of that. I mean, so it's kind of interesting, because again, I mean, you know, in a sense, if you only have Pauli's, then some sort of hard-nosed quantum computing or quantum complexity people would say, well, Pauli's are classically simulable, so efficiently, the Gottesman-Knill theorem. But on the other hand, you can leverage them into very characteristically quantum phenomena. Anyway, it's an excellent question, which I've also thought about, and I don't have a definitive answer. But of course, at this logical level, this kind of extra structure with some bit of the complex numbers, at least a multiplicative group of I or whatever, is not available to us. So at the level of partial Boolean algebras, it seemed reasonable that this was the key point. But and the way I would sort of feel we got to the point that we could say something like that if we were able to, for example, solve this challenge problem that I was mentioning about the tensor product, but we haven't got there yet.
Thank you.
But thanks for the question. No questions.
Okay, that seems good for the questions at the moment. So unless anyone else has anyone, I'll give you 10 seconds or forever hold your peace. And if there are no questions after that, then Samson, feel free to carry on from where.
Yes. Apologies for running on a bit, but anyway, if anyone needs to leave, then that's the good thing about Zoom meetings, isn't it? It's
okay. Yes. So it seems like there's no more questions for the moment. So yeah, please carry on, Samson.
Okay. Thanks. All right. So in fact, what we just for a moment to I've this thing again. Right. When I show the video panel, then I can't move the screen anymore, so I have to go through this rigmarole. Oh, let me my video panel view. Just want to see my whole screen while I'm using it. Okay, so what we were saying was that we have these Boolean algebra, partial Boolean algebra satisfying logical exclusivity, and in fact, we get that it's a reflective subcategory, and we sort of, as I said, we can sort of add the orthogonality from the original partial Boolean algebra and extend with that, but we need to keep doing it and sort of inductively close in order to get something that universally satisfies this logical exclusivity principle. And if we do that, then we get this result that we have a reflective subcategory. And in fact, again, we can sort of use that kind of workhorse construction that we saw earlier with the inductive construction. And there's, in fact, we can simply we can throw in an additional rule to the inductive system that whenever we have an instance of orthogonality, we add the orthogonality, the corresponding instance of compatibility. Actually, it's an interesting point that this is the sort of internal way of doing it by throwing it into the construction, the inductive construction concretely. We could also, in fact, take a co-limit along the things that we, these extensions where we extend by orthogonality and then extend by orthogonality again and so on, and the two things would end up in the same place. Okay, so having got this, we can then define a stronger tensor product which has more instances of the kind of things we want to get hold of and which we would need to get hold of in order to capture the Hilbert space tensor product. And so we get this this is a square box tensor product where we combine the weaker one we saw before with this reflection into the logically exclusive subcategory. And this is still sound for the Hilbert space tensor product. And in fact, we still get a Lax-monoidal functor with respect to this tensor product. So of course, the question is, how close does it get us to the full Hilbert space tensor product? And here, the answer is a bit disappointing, as we could ask if extending commeasurability by some relation can induce the Kochen-Specker property. And in fact, it can't. And this is simply follows from this kind of Kochen-Specker faithfulness of extensions, simply from the universal property of the extension. So if we have a homomorphism to a non-trivial Boolean algebra in the originally, then we would get one in the extension. And if we had one in the extension, then by composing with the unit map, we would get one originally. So, so we won't get this emergence phenomenon through this extension construction. There are still reasons why logical exclusivity is interesting, and it relates to, as I said, a very well-studied notion of a sort of probabilistic exclusivity principle, but I won't go into that. So anyway, we can apply this in particular to the tensor product. So if A and B are not Kochen-Specker, think of C2 and C2, then neither is this tensor product of them. And well, it's just what we were saying earlier. So we've narrowed but not closed the gap. So, right. So, well, as I said, there are a lot of probabilistic aspects. There's a whole, as I mentioned also, we were looking at the kind of the strongest contextuality property, what I call the KS property, but there is a hierarchy of notions and they come up very naturally in different ways. I mean, there's strong contextuality, which is very useful in many contexts. I mean, Kochen-Specker is strong contextuality to the max, where you it's a so-called state-independent strong contextuality. So you'd get a Kochen-Specker paradox just from the structure of the measurements, independently of which state you prepare. That's the very strongest kind. And then there are cases where you have state-dependent strong contextuality. And then there are weaker kinds. There's what we call logical contextualities. If you've heard of the Hardy paradox, that would be an example of that. Then you go all the way down to probabilistic notions, such as Bell constructions and others. One interesting point where logical exclusivity may be useful, and this kind of idea of extending things, is that we have a very nice connection between state-independent strong contextuality and so-called non-local games. So non-local games are a very well-studied context for quantum advantage, and there's recently been actually firstly beautiful results by William Slofstra, and then more recently a really spectacular result that goes by the name MIP star equals RE, which shows that multiple, it's a sort of IP is interactive proof systems with quantum resources is talking about. It turns out that that is actually non-computable. You get all RE sets can be described in this way. So that's a very spectacular recent result, which also simultaneously resolved a famous conjecture in quantum information, the Tyrolson conjecture, and the famous conjecture in mathematics, the Kohn embedding conjecture. Anyway, that's all very interesting stuff. We can relate Kochen-Specker style contextuality to non-local games, but there we take advantage of the fact that the contextuality is state independent. It would be really nice to be able to also bring state-dependent contextuality into this thing. And one idea is to sort of Kochen-Speckerize examples of, state-dependent examples of contextuality. So, and it may, and one idea is to use these exclusivity principles to do that. Yeah, anyway, yeah, I mentioned that there. Well, axiomatizing the tensor product. And actually, this is an interesting question, a natural question. One of the best known things about Boolean algebras is that you have stone duality between stone spaces and Boolean algebras. So it's a natural question. Is there some kind of nice duality for partial Boolean algebras? And there isn't an obvious answer because, of course, stone duality is all about points, and points are two-valued homomorphisms. And the point about interesting partial Boolean algebras is they don't have any points. So, but nevertheless, we believe that there is, so with Rui, we're working on we think we can get a result, which is a sort of a version for PBAs of the duality with some assumptions of the duality for complete atomic Boolean algebras. But that's still to be that's still work in progress. And also it would be, I mentioned these contradictions, the sort of conditions of impossible experience. So it's not that arbitrary contradictions can be realized, propositional contradictions can be realized in quantum mechanics. There's a certain rather specific class of these things. This is actually related to the duality question. So when you see discussions, kind of more concrete discussions in the physics literature of Kochen-Specker paradoxes, they're always talking about graphs. And it's essentially the contradictions are about, you know, graphs with certain coloring with a coloring problem, a Kochen-Specker coloring that can't be achieved, which is another way of talking about valuations, 0, 1 valuations on the vertices of the graph. And really one should think of those vertices as atoms for a suitable kind of partial Boolean algebra. So that's where the duality would come in. And the idea is to characterize exactly the contradictions that can be realized in quantum mechanics through this duality. So anyway, as I say, this is ongoing work. There's, to see what we have done, there's the paper, as I mentioned. Then I mentioned this binarity thing. So here's a nice quote from Specker. Do you know what, according to me, is, so Specker died a few years ago. Simon Kochen is actually attended the meetings of the 50th anniversary of the Kochen-Specker theorem. But here is something from Specker. What the fundamental theorem of quantum mechanics, you have several questions and you can answer any 2 of them, then you can also answer all 3 of them. This seems to me very fundamental. This is essentially the point we were making, that pairwise compatibility is a pairwise, or compatibility in the sense of commutativity is a pairwise condition. On the abstract level, you can certainly consider more general things, and in the sort of sheaf-theoretic context, it's very natural to do so. And there are lots of other examples coming from different places which are genuinely higher dimensional. Now, in partial Boolean algebras, this binarity is built into the definition because the compatibility relation is binary. But of course, you could consider some generalization of that, which allow sort of higher arity compatibilities. And in geometric terms, this would lead to higher dimensional phenomena. And, you know, there are really very nice topological aspects of all this, which I haven't touched on at all in this talk. So the question is about adapting the theory to this more general format, and how much of what we've been talking about carries over in a nice way. Okay, now I want to finish up with a mystery of partiality, and this is a result by Conway and Kochen. Now, Conway and Kochen sort of had some very well publicized work on the so-called free will theorem, which, and in my opinion, it doesn't. I mean, the name is great, right? But I don't think that result really lives up to the billing. But on the other hand, they have some really fascinating results which are not well known at all. And in fact, you can basically only access them by kind of transcripts of talks given by Simon Kochen. And I want to, which show how different partial Boolean algebras are to total Boolean algebras. As I was saying, you know, if you disregard the, you know, the sort of, obviously at some point you get into real higher set theory questions, but if you know, down below finite Boolean algebras, certainly everything seems very simple. So here's a standard fact: every finitely generated Boolean algebra is finite, because, you know, you can take normal forms, distributive normal forms, or disjunctive normal forms or conjunctive normal forms. And if you start with finitely many generators and up to logical equivalence, there are only finitely many of these. So here's this result. Back to P of C4, a wonderful setting where all kinds of wonderful things happen. In P of C4, there's a set of 5 projectors, local Paulis, just as sort of things that, you know, that Andreas was mentioning, as in the Mermin construction, which generate a uniformly dense infinite subalgebra of P of C4. So what they mean by uniformly dense is that, you know, you start generating just under the operations of compatible product and complement. And after n generations of, well, after n kind of steps of this generating everything you can, you're sort of densely filling the kind, if you think of the unit sphere, if you think of a vectorial representation, so you're getting, that close 1/2 to the n to every element in the unit, every vector in the unit sphere. And of course, I mean, it's an infinite subalgebra in the limit of that. And they use, I mean, the full proofs aren't there, but some very elaborate geometry and algebra is used to show this, which I'm certainly not familiar with. So things like root lattices of E8 and various various classic surfaces from projective geometry and so on. The sort of things, I suppose, that Conway and Kochen can see in their heads without too much effort. But anyway, what I would like to ask is there a logical proof of this? Because combinatorially, it's perfectly clear what's going on. I mean, we've even done some computations, to sort of generate things. The local Paulis are quite simple things to describe. So it's a generators and relations problem. There should be a sort of logical or combinatorial proof. I'll finish with that question. Thanks very much.
Thank you very much, Samson. That was a virtual applause. Thank you for that talk. Very interesting. Does anybody have any questions? If so, just post a little message in the chat. And while we wait to see if there are any, I've got a very naive question I would like to ask, which is kind of just to do with this kind of dimensionality requirement. So you mentioned, like, right near the beginning of the talk that, things start to really get interesting at dimensions like greater than or equal to 3. And you can kind of understand either side of this, because for 1 qubit, the difference between 1 qubit and 2 qubits is, with 2 qubits, you can start doing a lot of quantum things. Things don't show up until you have 2 qubits. Yeah. But is there some kind of nice physical interpretation for why things should work in dimension 3? Like why 3 dimensions is enough for these kind of properties to start showing up? Is there some kind of physical? Physically,
no, not that I know of.
Okay.
I mean, it's mathematically, if you think of also in projective geometry, various interesting things start happening in dimension 3. But physically, I have never seen, I mean, of course, you can always say that, if you go into low enough dimensions, various phenomena don't appear yet. But beyond that, no, I've never seen any kind of physical derivation of 3 there.
Sure. So we've got so David Yetter has asked the question. He says, is there a relation between this and quantiles?
Quantiles, right. It's well, of course, I mean, quantiles are in some sense, quantiles are, you might say to linear logic as Boolean algebras or complete Boolean algebras are to classical logic. And yeah, there's another kind of missing link. I think in the early days of linear logic, many people thought there would be a nice connection with quantum mechanics. And again, I've never really seen that. In quantum mechanics, we use all the time, the things like, well, in finite dimension, the fact that we're in a compact category, we have traces and we have scalars and all these things. So we're not sort of in a place where the full circumstances of linear logic show themselves. And I think the fact that locally we have a Boolean structure, I mean, because it's the classical world and we want to have, we do have in what we observe in the lab for particular measurements that we can perform, the observable things that are the family of data that we're then talking about patching together. I mean, that kind of should be classical probability. And the whole point of the Bell inequalities, which, as I said, relate to Boole's conditions of possible experience, is exactly based on that. So it's not clear why one would want to go towards. I mean, I don't see well, I suppose the short answer is no, as far as I can see, but just elaborating on that, that's what I would say.
Okay, thank you. Are there any more questions from anybody? No, it doesn't look like there are. So I'd like to thank you again, Samson. It was a lovely talk.
Thank you very much. Actually,
you.
can I ask a question? I mean, as far as, I mean, is this an open seminar?
I mean, yes. So what I was going to say now is I was just going to remind everyone briefly that there is not a Colloquium talk next week because there's the polynomial functor workshop. It's been moved to the week after on the 25th. But yeah, what I was going to do now is kind of, I'll finish the YouTube live stream, but I'm going to leave this Zoom room open so that people can just kind of have a discussion if they so wish. So yes, it will turn into a kind of open seminar.
Yes, but what I actually meant to ask was, can anyone join the Colloquium on future instances?
Oh, yes, definitely.
I mean, is it sort of advertised, or I mean, how does one do that?
This Colloquium, yeah, it is advertised. There's a mailing list for this. David, do you want to say a few words?
Yeah, thanks for asking, Samson. Let's see, how should we do it better is really the question. We do have a site called topos.site, so it's easy to remember, where we list the Colloquium every week, the colloquia. But I don't know, how would you have heard about it, Samson? What methods do you usually hear about these?
Well, I heard about it in this case because I was asked to give a talk by you.
Right. I mean, how do you normally hear about
well, I mean, it's a question because I don't kind of, yeah, I mean, I just by accident. So I suppose really what I'm asking is would it be easy for me to attend future instances?
We'll certainly invite
also, you. Should I feel, is it okay to recommend to students and so on that they might want to participate?
Yeah, certainly. So we'll send you an email with the details on.
Okay, that
we'll just add you to a weekly invite list.
Okay.
Yeah, and I would just reiterate the point, especially students. It would be great to get.
Yes, I have several who I'm sure would be very interested. Yeah.
Wonderful. And Brendan has posted some links in the chat for everybody else. So thank you, Brendan, for doing my job for me. That's great. Okay, I'm going to end the live stream now. But like I said, I'm going to leave this room open. So if anybody wants to stay and chat, you can. If not, you can leave, and that's wonderful. So thank you again, Samson.
Okay, my pleasure. Thanks very much.
Thanks, Samson.